Greetings from CC12. This is a video of Calculus 2 project, and these are our group members and ID. I would say that each member has actively contributed during the whole project. So next is our presentation.
Before we begin the first problem, we will learn about Lagrange multiply method. Lagrange multiply method is a technique for finding a maximum or minimum of a function f of xy subject to a constraint of the form g of xy equal to 0. Geometric basics of Lagrange multiply method can be explained if the functions are of two variables. So we start by trying to find the extreme values of function f subject to a constraint of the form g is equal to 0. In other words, we seek the extreme value of function f when the point xy is restricted to lie on the level curve g is equal to 0. Figure shows the curve g of xy equal to 0, together with several level curves of function f of xy equal to c, where c is constant. To maximize function f subject to g is to find the largest value of c such that the level curve f equal to c intersects with g is equal to 0. It appears from figure that this happens when these curves just touch each other. That is, when they have a common tangent line. This means that the normal lines at the point m x0, y0 where they touch are identical, so the gradient vectors are parallel. To solve this problem, we introduce a Lagrange multiplier lambda and consider the function f of xy lambda equal to f of xy minus lambda g of xy. The critical points of f are the solution to the system of equations. Fx of x and y minus lambda gx of x and y equal to 0, fy of xy minus lambda gy of xy equal to 0, and function g of xy equal to 0. The first two equations express the condition that the gradient of f is parallel to the gradient of g at the critical point, while the third equation enforces the constraint that the point xy lies on the curve t. The Lagrange multiply lambda is introduced to ensure that the constraint is satisfied at the critical point. Now, if we assume that f had a maximum or minimum value at a point m x0, y0 on t, then this point must be a critical point of L. This is because if m is not a critical point, then we can move slightly along t with the direction that increase or decrease f, contradicting the assumption that m is a maximum or minimum. Therefore, to find the maximum or minimum value of f on the curve t, we need to focus on the critical point of L that lie on t. These critical points satisfy the condition that the gradient of f is parallel to the gradient of g, which is exactly the condition given in the statement of the method of Lagrange multipliers. For the next problem, is it possible that Lagrange multiply lambda equal to 0? The answer is yes, it is possible for lambda to be 0. In fact, when lambda equal to 0, the equation will reduce to fx equal to 0 and fy equal to 0. It means that the gradient of the function f is perpendicular to the tangent of the curve t at the point x0, y0. These points are known as stationary points or critical points, and they can correspond to local maxima, local minima, or saddle points of the function f on the curve T. Therefore, it is important to check the second derivative test or the other method to determine the nature of the critical points at that.
So in this part, I will apply the Lagrange method to solve an example about evaluate the maximum and minimum value of this function on a given curve. First, we minus 1 to both hand sides to get the equation gxy equals to 0. And then evaluate the partial f with respect to x, y, and lambda, which is also gxy. Then we have these three equations. By the equation 2, we have y equal to 0 or lambda equal to 1.5 y squared. Put it here. And with y equal to 0, we substitute to the equation 3. Then we have x equal to approximate to this value. And in case lambda equal to 1.5 y squared, we have this after my substitute to the equation 1. And with the case x equal to 0, we can find y. But if x is different to 0, we can multiply both hand sides by y squared over 2x. Then we have this. Substitute to 1 and multiply both hand sides by 4x. And then I'll call this hx. I will do a fast evaluate to find hx is equal to 0. So note these domains and find derivative of hx. Draw a table and then hx equal to 0 has one solution. I'll put it here. So finally, we substitute all the stationary points we have to get these three values. So in conclusion, we can use the Lagrange method to evaluate the maximum and minimum value of fxy on a given curve. These two values. So let's move to problem 2. This is our group problem. I will summarize it using this illustration. So we have street A, street B, and street C. Street A and B have one common intersection, and street C is crosses between them. There is also a supermarket on street C. So the question is how can we construct a road in the most safest way, in the most safe money way that cross A and B and the supermarket at C. So in our presentation, we'll consider this is two infinite long road and have common intersection because this is too simple. So I'll use this illustration while discussing. We have some symbol. This is x, y, p1, p2, theta, pip parallel with b, and pbb parallel with a. So we need to minimize the value of this segment, which is the square of x is equal to x squared plus y squared and minus 2 xy cos theta. So by the conditional line segment, we have this equation. So minus 1 on the both hand side, and let's say this is fxy and this is gxy. We have this condition. So then applying the Lagrange method, we have discussed about, we have this. And by evaluating delta and partial fx, I'll know that we'll get the minimum value in this case. So we have this equation, and let's call t equal to x minus p1, and we finally have this. And Given the specific example, theta equal to 60, this small angle is 16.7, and SB is 2.1. Using cos formula, we can find P1 and P2. And applying the method we have proved above, we have t equal to this. Then we solve for x, y, and substitute to find the shortest line segment. So extending to AB is finite line segment. We apply the same method, but in the end, we need to check whether U and V are in the initial line segment AB or not. So this is the end of our presentation. Thank you for listening.